Hey, it's Justin, as you probably know by now, and this is, AP Physics, Chapter 1, Kinematics, Motion in One Dimension. In observing motion, there are two key things that we focused on: the observer and the object of interest. The observer can also be, an object of reference. Motion is a change in an object's position to a given observer or point of reference during a certain change in time. Motion pertaining position and time is typically described as an object's velocity. Below it is a motion diagram. Motion diagram is made to describe an object's velocity, like basically showing whether that velocity is decreasing, increasing, or not changing at all. Constant velocity. The graph below actually shows, a constant velocity. The acceleration of a system object should also be taken into account. Acceleration is an amount of how much an object is speeding up or slowing down over time. Meters per second squared is what represents acceleration. Earth's gravitational force is also a form of acceleration. This force causes an acceleration of negative 9.8 meters per second, which means a system object is always accelerating downwards unless on an even plane. Gravity enacts on a system object in most all cases. This is a sketch. It's used to create a clear representation of a situation. This is a motion diagram. It's used to represent the motion of an object. These are equations you may use when solving for certain parts of a problem pertaining motion. You can choose from either of these three equations depending on what variables you're solving for. Now, let's move on to a practice problem. Problem 79. Some people in a hotel are dropping water balloons from their open window onto the ground below. The balloons take 0.15 seconds to pass your 1.6 meter tall window. Where should security look for the Raskus hotel guests? In this situation, the window will be the point of reference. The balloon, the object in motion, is the system object. The object is falling downwards at gravitational speed. This is the motion diagram of the situation. The balloon is increasing in speed downwards. We will be using these equations to solve the problem. In order to find where the balloons were dropped at, we must first find how fast the balloons were passing the window, aka the initial and final velocities. These are our variables, and from what we can see, the only thing we're missing is the initial velocity. So, let's solve for that. From plugging in our variables and doing all that multiplying, addition stuff, we see that our initial velocity, is 9.8 meters per second. Okay, completely unrelated, but can we just, appreciate how nice this 9 is? Look, it's perfect, it's perfect. Now that we have the initial velocity, we can solve for the time it took for the balloon to reach that velocity. From a velocity of 0 meters per second. Ignore the bottom part for now, but these are our variables. From plugging in our variables, we see that the time it takes for the balloon to reach a negative 9.2 meters per second velocity from a 0 meters per second velocity is 0.94 seconds. Now that we have the time, we can now solve for the balloon's initial position. These are both the equation we will be using and the variables we will be plugging into it to solve for our position of where the rascals are at. From plugging in our variables into our equation, we now see the people throwing balloons are 4.33 meters above your window, from the top of your window. So now rat them out to security. In this problem, we had to assume that there was no air resistance and no obstacles in the way of the balloons.